Ladies and gentlemen, I'd like to welcome you to the first 1991 Beatty lecture. The Sir Edward Beatty Memorial Lectures were established in 1952, and the lectures were endowed by Dr. H.A. Beatty in memory of his brother, Sir Edward Beatty. Sir Edward Beatty was a former Chancellor of McGill University and Chairman of the McGill Board of Governors from 1921 to 1943. And he was also for many years the President of Canadian Pacific. The Beatty Memorial Lectures bring to McGill and to Montreal outstanding non-Canadian scholars to deliver a public lecture and spend time with faculty and students. Tonight's Beatty lecturer is Dr. Chen-Ning Yang. Dr. Yang was born in Anhui, China. He received his PhD in 1948 from the University of Chicago. From 1949 until 1966, he was professor at the Institute for Advanced Studies at Princeton. Currently, he is the Albert Einstein Professor of Physics at the State University of New York at Stony Brook, and is also Director of the Institute of Theoretical Physics at the same campus. He's the co-discoverer of the phenomenon or the theory of parity violation, for which he was awarded the Nobel Prize in Physics in 1957. He's also responsible for the Yang-Mills theory in physics relating symmetry and physics via the nuclear force and the weak force. And he is renowned for the Yang-Baxter equation, which describes the relationship between symmetry and two-dimensional statistical mechanics. For his outstanding contribution to science, Professor Yang has received many awards, including the Albert Einstein Commemorative Award, the Nobel Prize, the Rumford Prize, the National Medal of Science, and the Liberty Award, as well as numerous honorary Doctors of Science degrees from very distinguished universities and other accolades. Tonight it is a great pleasure for us to be addressed by Professor Yang on symmetry and physics. I'd like to welcome Professor Chen-Ning Yang to the Beatty Memorial Lecture.
Thank you very much. The concept of symmetry is clearly as ancient as mankind. If we ask how did it originate, we perhaps could guess that it came about in the following way. First of all, there are various natural symmetries that ancient human beings must have observed and must have been impressed with. And out of such observations, there arose man-made symmetry and the associated concept of asymmetry. And those ideas found their ways into various human activities, including the decorative arts, painting, sculpture, music, literature, architecture, in other words, all areas of early human activities. This slide shows you a 20th century photograph of various beautifully symmetrical snowflakes. But the early man must have been impressed by such a beautiful symmetry. Here is a slide made by a 19th century marine biologist of marine creatures, and you see that the one on the upper right exhibits almost perfect octahedral symmetry. The one, say, on the lower right has almost perfect dodecahedral symmetry, and so on and so forth. Out of such observations of natural symmetry, people extracted the idea of the symmetry, and in the next few slides, we exhibit some early examples of the human perception of symmetry. This is a Shang Dynasty bronze dating some more than 3,000 years ago, perhaps 3,300 years ago, and it has a beautifully graceful shape which shows the appreciation of the artists of the concept of symmetry. This particular bronze piece is now in the Freer Gallery of Art in Washington, D.C. Here is a picture of a mosque. The Islamic architects were famous for their appreciation of very complicated symmetrical patterns. Here is a slide of an ancient Chinese poem written by Su Dongpo, who lived about, I cannot get the focus correct, who lived about 900 years ago. I don't expect most of you to be able to read it, but the reason that I showed it is because the Chinese poem of this type are read this way. This reads 潮水暗浪雪山群. Then you go to the next line and next line and so on and so forth until you end up at this point. By the way, this was a beautiful calligraphy written by a friend of mine who is a famous painter. Now, the strange thing about this poem is that it's a very beautiful poem in the normal way, but it also could be read this way, from the bottom up, this way, and this way. And that's also a beautiful poem, and it's a different beautiful poem. Now, you might say that, well, there may be some ancient Chinese literates who had nothing to do, so he passed time by writing such a complicated things. So let's look at the next slide. This is by the great Johann Sebastian Bach. It's a violin duet. And if you look at the music of the first violin, it goes this way, ending up here. And that's the time reverse pattern of the second violin. I cannot tell which of these two compositions was more difficult for the artist to compose, but it is obvious that the fact that they devoted a lot of time doing this shows that they felt that the symmetry is an essential element of their work. The entrance of the concept of symmetry into science dates back to these people, to the Greek philosophers and mathematicians, to Pythagoras of the 6th century BC, and then Plato, Euclid, Archimedes. Many of these Greek philosophers and mathematicians had deep appreciation of the concept of symmetry. In fact, they had so much appreciation that they formulated the dogma of the harmony of the spheres, or the dogma of circles, which were a priori ideas with which they tried to construct the motions of the stars. And these had a profound influence on subsequent astronomy, and mostly a very bad influence, because it retarded the progress of astronomy for hundreds of years. This is a sculpture which you can find today in front of the great cathedral of Chartres in France, and this was supposed to be Pythagoras. The interesting thing is that he was left-handed, see? Now, Pythagoras and his school formulated not only the Pythagorean theorem, but they really launched the Greek science of geometry, which had profound influence on subsequent developments, including modern science, as we shall see later. One of the great discoveries of the Pythagorean school was the theorem that there are 5 regular solids which are most symmetrical, and there are only 5. And these are the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. In fact, some people said that the reason that the Euclid finally compiled the elements, one of the great classics in the history of mankind, was because he wanted to prove this theorem, that there are these 5 regular solids and only these 5. Indeed, if you look into the 13 books of Euclid, the theorem which states, this particular theorem, which I just stated, was the last theorem in the whole book. The Greeks were so impressed with the symmetry of these solids that they were, in some sense, obsessed with it. And they felt that everything in the universe must be constructed out of things which these 5 solids symbolize. And this is a certain philosophical drive, and you find it in all of the Greek philosophers' writings. Now, the Greek influence of this dogma of the circles, or of the harmony of the spheres, made the Greek astronomers spending a lot of their time trying to describe the planetary orbits in terms of first circles. When that didn't work, they made the circles on circles. When that didn't work, they made circles on circles on circles. And that tradition was perpetuated for more than 10 centuries. And eventually, Kepler was the person who broke out of that tradition. And yet, if you look into what Kepler wrote, you would find that he really started exactly in that tradition. It was only by a lot of studying that he found that he had to break out of that tradition and use the parabolic or elliptical orbits in order to describe the planetary motion. If you look into his first book, the Mysterium Cosmographicum, published in 1596, there were very interesting discussions of how he got into his later great discoveries. What he was studying at that time was the question of the ratios of the diameters of the planetary orbits. Now, at that time, there were 5. He had already accepted the Copernicus theory of the heliocenter system, and he knew that there were 6 planets at that time. And he felt that these 6 planets, the diameters of their orbits, must in some way be related to the 5 symmetrical solids. So he thought and thought about it, and one day he said he hit upon a brilliant idea. The brilliant idea was to have the orbit of the largest planet represented by a sphere. And then inside of the sphere, he erected a cube such that the corners of the cube would touch the sphere. And then inside of this cube, he put in a smaller sphere, which is tangent from the inside to the cube. The inside of this smaller sphere, he put in a tetrahedron, so that the corners of the tetrahedron would touch the sphere, and so on and so forth. Now, there are 5 solids, but 6 planets. But of course, in between the 6 planets, you would, represented by the 6 spheres, you would exactly put the 5 regular solids. Now, of course, you can permute these 5 solids, and there are 5 factorial equal to 120 possible permutations. So he ran through all of them and found that this particular one was the best, in the sense that if you do it in this order, namely cube, tetrahedron, then dodecahedron, and so on and so forth, you would find that the ratios of the diameters of these spheres, which he could compute, was approximating, as far as he knew at that time, the diameters of the planetary orbits. So therefore, he said this. He has therefore an explanation in terms of the 5 regular solids of the planetary diameters. Now, of course, we now know this is totally wrong, because in the first place, there are not just 6 planets. We know there are many more planets, and yet there are only 5 solids with which you can put in between the spheres. So therefore, the whole a priori reason was totally wrong. But this was what induced Kepler to think, according to himself, more about these planetary motions, and out of that there came the 3 famous Kepler's laws, and Newton later erected the whole edifice of modern mechanics on these Kepler's laws. So you see that although the Greeks' ideas were not quite right, it had a profound influence on Kepler, and therefore on modern physics. But I would add to that, before we laugh at this sort of prior method of Kepler's, I want to emphasize that this sort of idea of Kepler's is exactly what we do today, at least in one aspect of what we do in modern physics. We find many elementary particles, and they have some symmetry properties which are rather peculiar, and we know that they are mathematical symmetries, and we try to match the experimentally observed physical symmetries with the mathematical symmetries, and most of the time it doesn't work, and we permute the order of these very much like Kepler did, till eventually every now and then we would find one match, and then we would say, ha, we have understood something in terms of the symmetries. So the spirit is really quite the same. The methodology is also very similar. So we shouldn't laugh at this great failure on the part of Kepler. Kepler himself liked very much geometrical figures. This slide was taken from one of the books, and if you look at it very carefully, he had many very original ideas, original geometrical ideas, which have now in the 19th and 20th century come to the fore. The concept of tiling, which is a very important subject about which I have more to say. Kepler already had some initial ideas about the concept of dual solids. We know that if you take an octahedron has 8 faces, each of which is a triangle. If you take the 8 centers of these 8 faces, they form a cube. We say that the cube is the dual of an octahedron. Now, if you take the cube in turn, it has 6 faces. If you take the 6 centers of these 6 faces, they form the corners of a octahedron. So the octahedron is the dual of the cube. So they are sort of duals of each other. Now, this concept was already very much in some of the writings of Kepler. So Kepler was deeply influenced by the Greek geometric tradition, and he left that in turn as a heritage, which gave rise eventually to Newton's beginning of the science of mechanics. Now we jump a few centuries and go to the 19th century. A most important development in the 19th century in physics and in mathematics was the formulation of crystal symmetry, which took some 60 years, from 1830 to 1890. And simultaneously, there was the concept of the development of groups, starting with Galois in 1830, and then starting 1880, Sophus Lee generalized the idea of groups into what is now called Lie groups. These are tremendously important developments in the mathematical language. These latter two, groups and Lie groups, are provided very important language with which mathematicians formulate the concept of symmetry. Now, I don't think it's useful for us to go into details of groups and Lie groups, but I'll go a little bit into the crystal symmetry, both because it's quite understandable and also because out of it we get some spirits. We get some of the spirit of the concept of groups. In the next slide, I show two lattices. On the left side is a lattice which I shall call A, and it has many symmetries. By the way, you should regard this lattice as extending to infinity in both ways. In what sense do we say that it has a symmetry? Everybody who looks at it would say it's very symmetrical, but that's not enough for a mathematical analysis. We have to be more precise. In what sense is it symmetrical? Well, if I displace this whole lattice by 1 unit to the right, it evidently comes back to itself. We say that the lattice is invariant under such a displacement. If I displace it by 2 units upwards, it is also unchanged. So we say that that is also a symmetry element. So there are a collection of the symmetry elements which are displacements. If I move it to the right by 3 units, followed by movement upwards by 5 units, that's also a symmetry element. So mathematicians define all these as symmetry elements of this diagram. But these are not the only symmetry elements. I could rotate the whole diagram around this point by 90 degrees, and clearly the whole lattice comes back to itself. So the rotation around this point by 90 degrees is also a symmetry element. So is the rotation around this point by 180 degrees. If I take the center here and make a rotation around that point by 90 degrees, I get another symmetry element. So I get an enormous number of symmetry elements consisting of rotation. And I have more. If I reflect the whole lattice along this line, the lattice is not changed. So this reflection is also a symmetry element. So is a reflection along this line. So is a reflection around this 45-degree line. So there are many such reflection elements of symmetry. The totality of all these symmetry elements of this diagram is called a space group. And we say that this diagram belongs to that specific space group. Now, to appreciate the meaning of this concept of space group, let us look at this diagram. Now, this diagram is very similar to this, except that there are lots of alphabets D in different orientations added to this diagram. Now, it's obvious, if you just look at it, all the displacement symmetry elements of diagram A is also shared by diagram B. If I display B by 1 unit to the right, clearly it's not changed. So that displacement element is not only a symmetry element of lattice A, it's also a symmetry element of lattice B. In fact, all displacement symmetry elements of A are also symmetry elements of B. If I rotate around this point by 90 degrees, clearly this diagram is not changed. So a rotation around 90 degrees, by 90 degrees around this point is also a symmetry element of this diagram as well as this one. So therefore, if you look at it again, you would find that all the rotational symmetry elements of this diagram are also possessed by this diagram. But no reflection element, which is an element of symmetry of this diagram, is applies to this one. Because if I make a reflection around this axis, all the D's become B's, and there are no B's to be found in this diagram. So therefore, this diagram has less symmetry than this one. Its symmetry elements are all the symmetry elements which are displacements of this diagram, and all the symmetry elements which are rotations of this diagram, but none of the reflection symmetries obtained here. So therefore, this has a symmetry group which is smaller than this one. So I've explained in some detail the concept of symmetry as applied, of symmetry group, of space group, as applied to this one, and we said that there are two different space groups. This one's space group is smaller than this one. Now, why was that important for physics? Because people began to study crystals, and then gradually through 60 years of effort, they finally understood some fundamental truth. Namely, each crystal has a certain symmetry. It belongs to a symmetry group. And two crystals which belong to the same crystal group has much of their physical properties identical. So this classification into space groups is the most important subject. And they spent years quarreling with each other about exactly how many different space groups there were. Now, to understand the meaning of that sentence, let's look at this diagram. This diagram has 17 patterns. If you count 1, 2, 3, 4, altogether there are 17. And if you look at this diagram, the symmetry elements, the space group for this diagram is exactly the same as that of diagram A in the previous slide. The symmetry elements of this diagram is exactly the same as that of lattice B of the previous slide. So two space lattices are exhibited here as belonging to these two. Now, it's very easy for you to convince yourself that each of these has a space group. For example, this one has a six-fold symmetry. If you rotate this diagram, every diagram is imagined to be extending both ways to infinity. Now, if you like your bathroom floor, your bathroom floor belongs to one of these 17. This one is very peculiar because around this point, if you rotate around this point by 60 degrees, you get an element of symmetry. So evidently this symmetry is different from this symmetry. But a profoundly beautiful and important theorem was that there are no others. That any bathroom floor pattern has symmetry elements which is identical to that of one of the 17. This is a highly non-trivial theorem and a beautiful theorem proved in 1891. By the same sort of argument, but in a more complicated fashion, they also proved that there were 230 space groups in 3 dimensions, and therefore there were 230 different kinds of crystals. First, in 1890, Fedorov of Russia, Schunflies of Germany, and Barlow of Great Britain showed that in 3 dimensions there are 230 space groups. They looked into the 3 dimension first because they were interested in crystals, which are 3-dimensional objects. Then they decided, why don't we look at a simpler problem, namely the same problem in 2 dimensions. The next year, Fedorov showed that there are 17 of these, and these 17 are the ones I illustrated in the previous slide. Then, at the turn of the century, the great mathematician David Hilbert posed a problem, one of his famous 23 problems for the 21st century. One of these problems was to prove that in any dimension, the number of different symmetry space groups is finite. And that was rapidly proved by Bieberbach within 10 years at the beginning of the century. But the precise number for higher dimensions was difficult to figure out. Finally, in 1970, it was figured out that in 4 dimensions, this number is 4,895. This figure is very difficult to figure out because people don't have 4-dimensional vision. And it finally settled down to 4,895 after a lot of quarreling because with the aid of the modern computer, it was able to count this number. Subsequent dimensions all are finite because of the Bieberbach theorem, but the precise numbers are not found yet. There are upper and lower bounds, but they are not found. Now, what I've talked about so far, I have already touched on the idea of the group. And as I said, the idea usually is said to originate with Galois. Actually, much before Galois, Lagrange and Cauchy already had ideas of the group, but it was Galois, as a young man, who really made use of the concept of groups, and that has a profound influence. And when Sophus Lie generalized it in 1880 to Lie groups, these two ideas have formed a central concept in 20th century mathematics and also in 20th century physics. In 20th century physics, because groups are the natural language with which, natural mathematical language with which to describe the physical concept of symmetry. Now we go into 20th century. And I want to emphasize 2 points. The first point is that the symmetry used in physics was enormously enlarged because in quantum mechanics, the mathematics is linear. And we'll elaborate on this a little bit later. The second point is that symmetry use was transformed in this century so that the principle that symmetry dictates interaction became prevalent. And in the next part of my talk, we would be elaborating on these two themes. This is a slide which was made in 1957, which described the position of symmetry in physics up to that time. Symmetry and invariance, words which we have touched upon previously, are very much related concepts. And out of that, I put a box here called other consequences, and that includes such things like the classification of crystal symmetry into 230 different space groups. But in the 20th century, this gets shunted aside, and the central use of the concept of symmetry followed this line. Because of the concept of symmetry, there arose conservation laws, like the conservation of momentum and the conservation of angular momentum. The conservation of momentum and the conservation of angular momenta are very important, and they were known already since Newton's times. But that they are related to the concept of symmetry was not appreciated until this century. In the first 20 years of this century, physicists and mathematicians finally understood that these conservation laws, which have been used a lot, these symmetry concepts which were vaguely appreciated, were in fact deeply related. And out of the fact that symmetry has something to do with conservation laws, there arose deep concepts called quantum numbers and selection rules. These are in fact these provided the very language with which we describe atomic, molecular, nuclear, and elementary particle states. So therefore, the concept of symmetry had crept into the very language of physics. Well, in the next slides, I show you a few very simple examples of how with quantum mechanics, with the concept of symmetry, we have understood many things. This is the famous periodic table, and we all knew it played a very essential role in the progress of chemistry in the latter part of the last century and the early part of this century. But what is the nature, what is the origin of these periods, 2, 8, 18? They were just phenomenologically fitted because of the chemical properties of the different elements, which suggested to Mendeleev that he should put them into columns, and then out of these columns, these numbers, these periods, 2, 8, 18 came about. But when quantum mechanics was born, when symmetry became related to conservation laws and related to quantum numbers, it became rapidly clear that these numbers came out of the mathematics of rotational symmetry. This is a most beautiful explanation of the periodic table on a more profound level than the phenomenological one. Another example that I can give, I would start by telling you, by reading you this statement of the great biologist Monod, who said that the discovery of the dodecahedron and icosahedron, apparently made around 600 BC in one of the Greek colonies of southern Italy, is considered by Hermann Weyl as one of the greatest and most beautiful in the whole history of mathematics. The viruses apparently made this discovery much earlier. What the Monod was referring to was the fact that in the late 50s, Crick and Watson in a paper, not the famous paper about the double helix, but in a later paper, showed that for reasons of economy, viruses might form into dodecahedron or icosahedron. And that conjecture was later found to be correct. This is a electron micrograph of some of the virus particles, and when you enlarge them enormously, you find that they indeed are very symmetrical. And here, you see the dodecahedron and the icosahedron are duals of each other. So they can be merged very easily. This is the dodecahedron, this is its dual, the icosahedron, and they can be merged, and after merge it's like this. And indeed, when you have a high-powered electron micrographs, you find that some of these virus particles look exactly like this. In 1957, there was the great excitement due to the experimental verification at the Bureau of Standards by C.S. Wu and Ernest Ambler and their collaborators, that the right-left symmetry was not observed in beta disintegration. The principle of the experiment was a very simple one. Namely, you construct two sets of equipment which are mirror images of each other, but not identical. And here's a cobalt nucleus, here's its mirror image, a cobalt nucleus, and here's a counter which detects the beta decay. If you only have the equipment which I just named, then the two experiments are the same. They are mirror images of each other, but they are also the same experiment. So there cannot be any differences. But if you put a coil around here with a current going this way, then the mirror coil would have a current which goes this way. Now, the mirror image experiment and the original experiment are not the same. So therefore, they could be different. And when they tested this, indeed, it was shown that right and left were not symmetrical. Exactly. They were almost exactly symmetrical, but not quite. And that small difference was what they were looking for. So this showed that nature observes the symmetry very accurately, but not perfectly. And this led to many extremely important work in elementary particle physics. Here's a picture of the equipment that Ms. Wu and Dr. Ambler used, and this is now in the Smithsonian Museum in Washington. The discovery of parity non-conservation caused great excitement among the physicists, and everybody felt that the concept of symmetry and the slight defect in the concept of symmetry must have something to do with the structure, fundamental structure of particles. So Heisenberg and Pauli, two towering figures in 20th century physics, began in 1958 to construct a theory based on the concept of symmetry of everything. And later on, in 1971, after Pauli has already died, Heisenberg recorded in his book about that period, he said, with every step, that's in 1957 and 58, Wolfgang, that's Wolfgang Pauli, took in this direction, he became more enthusiastic. Never before or after have I seen him so excited about physics. Unfortunately, the path that they launched into was not quite right. So the symmetry, the equation, the symmetrical equation that they wrote down was not the right one, and their work is now only of historical interest. The great excitement about the symmetry in the 50s and 60s is further illustrated in this slide in the so-called eightfold way. It is a symmetry, a more complicated symmetry than has been discussed before that time, and this was something which dominated elementary particle physics in the early 1960s. This diagram I took from an article written by German and Chu and Rosenfeld in the Scientific American magazine. Now, I had previously shown the position of symmetry in 20th century physics like this. Now we are 30-some years after when this picture was made. That was 1957. And today we have to enlarge this influence, and we have to greatly extend the influence of symmetry and invariance in physics, in fundamental physics, by adding this part. And the new words introduced are gauge symmetry and the concept that symmetry dictates interactions. There are 4 fundamental interactions: strong force, electromagnetic force, weak force, gravitational force, and it's now universally accepted that all of these are governed by the concept of symmetry dictates interaction, which symmetry is a gauge symmetry. So I'll spend the next 10 minutes or so giving you a kind of a general feeling of what the gauge symmetry is all about. We should go back to Einstein, because Einstein was really the first person who had utilized the concept that symmetry, out of the concept of symmetry, you can get equations of motion, that the forces of nature, in his particular case gravitational forces, how it operates, the mathematics of gravity is dictated by symmetry. This principle was the one that was first invented by Einstein. Einstein, in his autobiographical notes, mentioned about what gave rise to this kind of thinking. He said that if you look into electromagnetism, which was the most important discovery of 19th century physics, you would find that historically it went this way. First, through this 80 years of experimentation, there arose the 4 fundamental laws of electromagnetism. Out of those 4 laws, Maxwell in 1865, actually it's 10 years around that time, wrote down Maxwell's equations, which were mathematical expressions of the results of these earlier experiments. Maxwell's equations were not quite understood in Maxwell's time, and in fact for many years after his death. It was only in 1905, 40 years after Maxwell's equations were written down, that people found that there was a symmetry of Maxwell's equations. And that symmetry now is called Lorentz symmetry. And the one who really anchored this idea was Einstein himself in 1905, when he was 26 years old and invented special relativity. He said in his autobiographical notes that this so impressed him, he then began to ask whether we should turn the table around and go, instead of from experiment to equation to symmetry, go from symmetry to equation to experiment. And so he argued that maybe we should take some symmetry and ask what equations are consistent with the symmetry, and then derive what are the experimental consequences of these equations. And that is exactly what he did. It took him 8 years, from 1908 to 1915, to go through this process, arriving eventually at the general theory of relativity. So this idea to start from symmetry and ask what forces or what equations of motion are consistent with the symmetry, and then derive the experiments, was a tradition really started by Einstein. What the symmetry that Einstein chose was symmetry under coordinate change. This is a very large symmetry. I shall not explain this in further detail, but it was something which was fruitfully carried out in 1916. Then, 2 years later, Hermann Weyl, a great mathematician, tried to incorporate into Einstein's symmetry ideas something which he called abelian gauge symmetry to explain electromagnetism. In 1954, this abelian gauge symmetry idea was further generalized into what is called non-abelian gauge symmetry. Now, non-abelian gauge symmetry is much more complex and much more rich in its structure than abelian gauge symmetry, and all of these modern ideas of symmetry dictates interaction are using various types of non-abelian gauge symmetry. So this is sort of a skeleton history of how this idea that symmetry dictates interaction came into being in this century. I've now to explain this a little bit more in detail. In 1916, after general relativity, Einstein has said we have a satisfactory theory of gravity. Now, at that time, there were two kinds of forces known, namely electromagnetism and gravity. Weak interactions and strong interactions were not yet known at that time. And Einstein said, however, we must amalgamate these two forces to have a unified theory. And Einstein said that the space-time concept explains gravity, and we need to explain electromagnetism, so we need some idea here. A geometrical idea to be married to space-time so that the whole thing would explain both gravity and electromagnetism. But the question is, what is this question mark? And Weyl came out in 1916 and said that this question mark is local scale invariance. I shall only roughly say that what the Weyl said was that if you move from a point x mu to a neighboring point x mu plus dx mu, then a field function acquires a certain addition. If you now further change the scale of your physical quantity f, if it has the scale of 1 here, it becomes slightly larger in the next point, and you multiply the scale onto the field quantity, so therefore 1 times f you get f, this times this you get this expression, drop in the higher order terms, and so therefore you have this expression, which Weyl said is very similar to, in some respects, to electromagnetism. So he tried to identify this S mu with the electromagnetic potential. This idea he communicated to Einstein, and Einstein objected. As a consequence, when the paper of 1918 of Weyl, which is of historical importance, was published, it had a postscript by Einstein. Einstein said that Weyl's idea is very ingenious, but it's totally wrong. Because Einstein said, according to Weyl, when you move from one point to the next point, the scale changes. So he said, let us imagine that we have 2 meter sticks at the same space-time point, and we move one of them around this loop, so it returns to this position, and we move the other one, which had the same length originally, around a different loop, so that they come back to the same space-time point. Now, because they follow different paths, according to Weyl, they would change their length differently, so by the time they come back, they would not have the same length. Therefore, you cannot standardize meter sticks, because meter sticks' length would depend on their history, and therefore the whole physics would collapse, because if you have no way to standardize your meter sticks, you cannot do any physics. Now, very unusually, the editors of the journal allowed Weyl to add a postscript after Einstein. And the postscript I read very carefully, in which Weyl said, Professor Einstein's criticism is not relevant because he did not understand what I mean. I read very carefully what he said afterwards. He didn't really say what he meant. So Weyl only said that Einstein did not understand him, but he did not explain what is it that he really said. Actually, Weyl came back to this subject in quite a few publications in subsequent years, but he really could not answer Einstein's criticism. Well, I would not be telling you the story if that's the end of it. What happened was that a few years later, completely independently in 1925, quantum mechanics was developed. And in quantum mechanics, you replace the momentum operator p mu by differential operator minus I h bar delta mu. And so London and Fock pointed out in 1925 that if you do that, then this operator, which is very important in physics, would naturally become this operator. And therefore, you would have this operator. Then they compared this expression with this of Weyr and said that, haha, Weyr was exactly right, but his identification at the last point was wrong. The S mu should not be identified with E mu, E times A mu, but should be identified with this. Now, this is almost the same as the Weyr identification, except for a very essential point, and that is the I here. Now, I is square root of minus 1. So, a square root of minus 1 was inserted into Weyr's idea, and as a consequence, the scale change of Weyr has become a phase change. So, Weyr called his theory a gauge field. That from today's viewpoint is a misnomer, because there's no size change at all. There's only a phase change. And gauge transformation is the term that we use today. It should not be called a gauge transformation at all. It should be called a phase transformation. But of course, we have been using the word gauge transformation for so long. Today, nobody in his right mind would try to change it. But it is important to realize that what is called gauge transformation, what is called gauge field, are really phase transformation and phase field. Now, once we understand this, there's something extremely interesting, because we can now revisit Einstein's 1918 objection. Einstein said that if you take two rulers and go around, one this way, when they come back, if a Weyr were right, they would not have the same length, so therefore physics could not be a science. Now, with the I inserted, when you have two identical rulers, with one going around this way, one going around this way, when they come back, they would have different faces, but they would have the same length. So therefore, Einstein's objection no longer obtains. But you could ask, okay, if they have different faces, does that difference of phase have any physical manifestations? The answer is yes, if you can interfere them. Of course, it's difficult to interfere two meter sticks, but you could imagine you can interfere two electrons. So if you have two identical electrons and move one around here and one around here, so they come back, and then you interfere them here, you would be measuring their phase difference. In particular, if you put a magnetic solenoid here with a flux coming out of the screen, then that interference would depend on the flux inside. And that is the famous Aharonov-Bohm experiment. Aharonov-Bohm, without reference to Einstein's paper, Einstein's objection of Weyr, without any of this history that I was telling you, independently proposed in 1959 the famous Aharonov-Bohm experiment, which was in a preliminary way proved by Chambers in 1960. And now in retrospect, after we have understood all these, we realized that indeed this Aharonov-Bohm experiment and Einstein objection are really, with the I inserted, are really the essence of the science of electromagnetism. Now, lastly, I want to make a very important point about the difference between the usual symmetry and the gauge symmetry. A usual symmetry is like a rotational symmetry. A gauge symmetry is what we've been talking about in the last 15 minutes. They are great similarities. They are all symmetries of some type, but there are also great physical differences, and it's important to keep that in mind. In the usual symmetry, let us say the symmetry of the orbital motion of a planet around the sun, you have the motion, the equation of motion of the planet around the sun, and out of that equation you can have many solutions. For example, you have one elliptical solution that I wrote that here symbolically, And if you rotate that elliptical orbit, you would get a different ellipse, and that's also a solution because the original problem is rotationally symmetrical. So you can rotate the ellipse and get many, many solutions, all of which are related to each other by symmetry operations, namely by rotations. And they all satisfy the same equation. The important thing is that these different orbits describe different physics. An orbit which is this way is, of course, different from an orbit which is this way, and different from an orbit which is this way. Although they are physically related to each other by rotation, they are different. They describe different physics. In gauge symmetry, you write down an equation, and you also have solutions which are related to each other by gauge symmetry, just like these solutions are related to each other by rotational symmetry. But the important thing is that in this case, all these different solutions describe the same physics. So this is a very different kind of symmetry. The symmetry here is you use different mathematics to describe the same physics, while here you use different solutions to describe different physics. And the very fact that all these different solutions describe the same physics says that your equation cannot be very random. If your equation is too random, you do not have this property. So therefore, the gauge symmetry is really a kind of a concept which limits the type of equations that you can write down, and that is the reason why it dictates the forces, because the forces are the key elements of the equations. And if the forces are not written down correctly, they will not have this property. So therefore, gauge symmetry is a concept which is ready-made to select the right forces, unlike the usual symmetry. This is a very important difference to bear in mind. Now, let us ask the question, a natural question: what should we expect in the 21st century? If we observe what has happened in the 20th century, we found that the tremendously sophisticated mathematical concepts came to the rescue of physics, and special relativity was based on four-dimensional space-time, general relativity was based on Riemannian geometry, quantum mechanics was based on the concept of Hilbert space. This is a misspelling. Gauge field is based on the beautiful new mathematical concept of fiber bundles, which came about through the mathematicians' studies starting from the 1940s or 1930s and 1940s. This progression of more and more sophisticated concepts make most of us believe that physicists will be borrowing more from mathematics, especially in the area of more symmetries. And that is the reason why in 1973 there was the very exciting and interesting idea of supersymmetry. 1976 it was generalized to supergravity. In 1984 there was the new development of superstrings. All of these are manipulations of the concept of symmetry and of field theory in order to gain experience with the variations of the idea of symmetry and see whether with the aid of these new concepts we could solve some of the still existing difficulties. I would conjecture that these type of activities would increase into the next century. In 1867, at the death of Faraday, whom Maxwell greatly admired, in fact, Maxwell felt that his contribution was to have written down the physical concept of Faraday into mathematical form. Faraday was 40 years Maxwell's senior. So Maxwell, in his obituary article about Faraday, had this to say: the way in which Faraday made use of his idea of lines of force in coordinating the phenomena of magneto-electric induction shows him to have been in reality a mathematician of a very high order, one from whom the mathematicians of the future may derive valuable and fertile methods. From the straight line of Euclid to the lines of force of Faraday, This has been the character of the ideas by which science has been advanced. And by the free use of dynamical as well as geometrical ideas, we may hope for a further advance. We are probably ignorant even of the name of the science which will be developed out of the materials we are now collecting. Indeed, he was so right. Nobody has heard of fiber bundles. Nobody has heard of Hilbert space or space-time manifolds at Maxwell's time. I'm sure that a century from now, we will find that additional manifestations of the concept of symmetry will become part of physics, and they will have names which today we do not know. Thank you.
Professor Yang has kindly agreed to take a few questions, so I'll open up the floor to questions or discussion. Yes.
You talked about the asymmetry you see in living systems, at the molecular level at least, everything is asymmetrical.
Yes.
That strikes me as critical reasons to Maxwell, but I'm not so sure.
Well, that's it's a very important subject, and I know that there have been a lot of speculations about it, but I'm not an expert on it. There are people who claim that the slight variation, the slight change between the right and the left, the slight difference between the right and left due to weak interactions, may have something to do with the fact that the glucose, the sugar that we see, is one-handed and not the other-handed. But I've not examined those speculations. I can only say that I don't think they are generally accepted yet. Louder. Are you asking, is it possible to explain that more in detail? Is that the question? Well, the atoms are spherically symmetrical because the fundamental equations governing them are spherically symmetrical. The spherical symmetry in the language of the mathematicians give rise to they form a group, and there's the concept of the representation of this group, and the representation has dimensions, and out of these dimensions you naturally get the number 2n squared. And if n is equal to 1, you get 2. If n is equal to 2, you get 8. If n is equal to 3, you get 18. And so it naturally comes from this representation theory of the group. It's SO3.
For a layman, an old man, I'm not a mathematician, and when you write down these very, very equations, which are worse than Chinese for me as far as understanding, would it be possible to express those very ideas in layman's language so that a person with not a great intelligence, but with a normal intelligence, would know what it means?
It's a very good question and a very important question, and I will try my best to answer that. Some of the equations are difficult, and I think that it's not very fruitful to try to explain them to people who have not studied a lot of physics. However, some of the very important equations can be explained. For example, some of the most important equations are Maxwell's equations. Maxwell's equations is the foundation of electricity and magnetism, and you can write them down. There are 4 lines of the equations. each symbol in it can be explicitly explained to a layman. So, because each quantity in it represents some measurable quantities, and one can explain how each quantity is measured. The two most important quantities in it, one is represented by capital E, the other is represented by capital H, and both of these are measurable quantities, and one can describe what type of experiments measure them. And indeed, that is how those equations were written down. So, from this viewpoint, the equations are abstractions of experiences which were learned through decades of experimentation. So, I think a layman is entitled to say what are all these fancy notations standing for. But believe me, they are abstract representations of very concrete experiences which derived from decades of experiments. And as I said, it took about 80 years from 1780 to 1860 that these experiments accumulated into 4 fundamental laws of physics. And then it took Maxwell 10 years to write them into mathematical form. And there was born Maxwell's equations. And this was the greatest achievement of physics in the 19th century. And in the 20th century, Einstein taught us how to interpret this and gave rise to the idea of symmetry, and which has now greatly blossomed into additional developments. Louder, please.
Yeah, the symmetry is natural of almost many things. Do you think that it's stable for the material is stable with the symmetry? And what is this first question? Stable related to the symmetry. Second is in our world there are many defects, not very good symmetry. What happened? The second. Some operators with the conjugate related to symmetry. That's the question.
Well, I'll concentrate myself onto the first two questions because I don't really understand the third question. Now, you talk about the stability of this symmetry. Presumably, you think that if you draw a circle, it's very symmetrical, but suppose the circle is, say you draw a circle on a piece of paper and put it on the surface water, then it's disturbed and then it's no longer symmetrical. But that's not the type of symmetry we are talking about. What we are talking about is the very symmetry of the equations themselves. Now, the amazing thing is that it's mostly symmetrical, but there are some asymmetry. And actually, this afternoon I've talked about both of them. The symmetry dictation principle adheres to the symmetry. But every now and then we find that the symmetry is not exactly true, and that was the case when it was found that the right-left symmetry was not exactly observed. Why are there these symmetries? Why are there these small defects? These are some of them understood, some of them not yet understood. But that both of them play essential roles in our perception of the physical universe, there's no doubt.
Very stable stability. For instance, that we call crystal, something like this, stable there. Another thing.
No, you are talking about, for example, the stability of a symmetrical solution. We are talking about the symmetry of the equations themselves. So these are two different things.
Yeah, I have a question about the first thing. Some people believe that super three is the figure of everything, and some other people just believe it. What's your opinion on that?
Did you understand? Louder.
Are superstrings
Oh, superstrings.
or not?
Theory of superstrings.
Oh, is the question whether the superstring theory is okay or is believable? Is that the question? Yeah. Well, the heydays of the superstring theory is over. It was sort of trumpeted as a theory of everything, and when you get very enthusiastic, bright people, they are likely to talk that language. But what has been learned are very interesting structures related to symmetry, but so far it has not found practical applications yet. It won't completely die because the beauty of the mathematical structure may recur in metamorphosed form in the future. But at this moment, it is sort of not the center of attention anymore.
That's the last question.
Yeah.
Are there significant differences with respect to representation, cultural representation of symmetry from culture to culture, in architecture, in art forms, and so on?
Well, that's a profoundly interesting and important subject. I'm certainly not qualified to speak about it, but I would say that in different cultures, the appreciation of different aspects of symmetry are clearly different. The very fact that the decorative art in different cultures tend to emphasize different things is a explicit manifestation of that. Now, I do not know whether your question also has the implication, are there cultural differences among the physicists which allowed some of us to emphasize one kind of symmetry, other of us to emphasize another kind of symmetry. In fact, in 1957, when there was all these discussions of right and left symmetry, I received letters saying, did your Chinese cultural background make it more likely that you land on this idea that right and left are not symmetrical? I remember thinking about it and answering those letters by saying, I thought about it, and to my knowledge, I didn't see any difference.
Professor Yang, we would very much like to express our appreciation for taking us through the history of how the understanding of the relationship between symmetry and physics has developed, and the evolution of this from experimentation to equation to appreciation of symmetry, and now the symmetrical presentation with looking at symmetry to then plan experiments and equations. And I think we greatly appreciate the insights that you've given us. Thank you very much for this lecture.